All right, here we go into another video on the derivative of the natural log. In this one, we're going to go over a couple of what I call old school concepts. Imagine that. These are now old school for you. So we're going to find the equation of a tangent line. Natural log is going to be involved. And then we're going to do a problem with relative max and min, concavity, all that good stuff. Again, natural log is involved. So old concepts, new function. Okay, so this says write the equation of the tangent line to f of x equals all of that at the point 0, 5. So what do we need? I always like to start out with my template, right? I know, at least in my head, I've got y minus y1 equals m times x minus x1. That point slope form is what I'm going after right here. So I'm going to take a derivative. I need to know my slope. So I'll do that work off to the side here. So f prime of x is equal to the derivative of 5, 0. The derivative of minus 2x squared, minus 4x. The derivative of, well, minus ln will be minus 1 over stuff, so it's 1 over 3x plus 1, times the derivative of that stuff, the chain rule involved there. And so it's going to be minus 4x minus 3 all over 3x plus 1. Not so bad. So now from here, what we need is, we need the derivative at the point 0, 5. So I'll plug in 0, f prime of 0. Well, 0 plugged into here is 0. Then we're going to get negative 3 over 3 times 0, plugging in 0 here, is 0 plus 1. Ah, that's very nice. That's going to be negative 3. So it's not a bad number at all. And we just plug it into our tangent line equation. Y minus y1 is 5 equals the slope, negative 3, which we just found with the derivative process, and then x minus 0. That's it. That's your answer. Okay, so got another part to the video. Like I said in the beginning, we're going to be going over how to find the where a function's increasing and decreasing. It says determine the intervals over which the following function is increasing or decreasing. Then find any relative extrema. Then determine the intervals over which f of x is concave up and down. So we're going to be doing a lot, basically going through a tour of a lot of what we did earlier with derivatives. It's not bad though. So if we want to figure out where a function is increasing and decreasing, we need to find its derivative, figure out where it's positive and negative. So f prime of x is equal to, product rule, first d second. Derivative ln x, 1 over x, not so bad, plus second d first. So that'd be just plus ln x. Now that's a weird number, I get it. The x's cancel and you get 1 plus ln x. Now when you're doing problems like these and you're determining intervals, I think it's really beneficial to start out by first noting what the domain of the original function is so that we don't go checking values for our intervals that don't apply to the function. So ln of x is in here, and if you remember, that domain is all numbers greater than 0. So x is greater than 0. And if you don't remember that, I go over y in video 1 of this lesson. Very cool stuff. All right, so 1 plus ln x is f prime of x. As always, we're going to set that equal to 0 or find out where it does not exist. Now, ln x exists everywhere on its domain. So it's not going to not exist. However, that's going to be equal to 0 when? Well, that would be when ln x equals negative 1, subtracting 1 from both sides. And then I'd exponentiate both sides to figure out what the x value is. Ugh, it's a weird number. E to the ln x, they undo each other. We get x equals e to the negative 1. And e to the negative 1 is the same as 1 over e, which is a positive number. So our number line, I put a vertical line here to say, hey, stop at 0, right? Don't include it. And then 1 over e is not very far after. And it keeps going on and on forever. So remember, this is f prime, and this will tell us details about f. Okay, so where are we increasing and decreasing? Well, let's pick some values here, and we'll plug them into this. Let's pick a number less than 1 over e. Well, what would that be? Well, this is e to the negative 1. Right, that's what that is. So let's pick like e to the negative 2. I know it's a weird number, but if I plug in e to the negative 2, we'll do that work off to the side here. 1 plus ln of e to the negative 2. These cancel, and you're left with negative 2. The ln and e cancel, and that's less than 0. That's all we cared about, right? So we know we're decreasing on that interval, 0 to 1 over e. And then from greater than 1 over e, I don't know, 15 billion? The ln of 15 billion is positive, plus 1 is still positive. So we're increasing everywhere thereafter. Okay, so what do we say now at this point? Well, a couple of things. We're decreasing, and I'm not going to like formally justify this. We're decreasing where f prime is less than 0. So if you had to formally justify it, you say that. So we're decreasing on, and it would be 0, to 1 over e. We'll do that in interval notation. And then where are we increasing? We're increasing on 1 over e to infinity. That's it. Now, where will there be a relative min or max, if any? Well, since f prime changed from negative to positive, at 1 over e, we've got a relative minimum. Okay, so again, I'm not asked to justify here. I'm just going to give my answers. You get the relative minimum at, and so that's 1 over e, and it didn't ask for just the x value. We need the y value as well. So we're going to plug that into the original function. So how do we do that? Well, I think it's easier to plug it in like this. I'll do it off to the side. X ln x. That's the same as plugging in 1 over e, or e to the negative 1, times ln of e to the negative 1. And ln of e cancels, and you give a negative 1. So negative e to the negative 1, which is negative 1 over e. That's it. That's your relative minimum there. Okay, next we're told, determine the intervals over which f of x is concave up or concave down. Now this derivative, which we're going to need to find, is actually not so bad, right? We've got f prime is 1 plus ln x. So f double prime, I'll do the work right here, is going to be equal to the derivative of that. Well, the derivative of 1 is just 0. And the derivative of ln x we know is 1 over x. Now, this is never equal to 0, ever, right? And also, remember that the domain we got to consider on our sign chart has to be greater than 0, because the domain of the function is greater than 0. So here's the thing. This is undefined, or DNE, at x equals 0. But there's no numbers below 0 we have to consider. So we're good. We just have to test a value to the right of 0. There's no other places where the signs of f double prime could switch. Okay, no problem. So that's f double prime. Talk about what's going on in f. Pick a random test point. Let's do 15,000. 1 over 15,000 is positive. F double prime is therefore positive the whole time. So we're concave up. So I'll say concave up, and that's on 0 to infinity. That's it. That's not so bad. Not at all. All right. So that's it for this problem. You go piece by piece. Notice that the way that we analyze everything with the first derivative and the second derivative, that doesn't change. So if you need review on why f prime being positive is increasing, negative is decreasing, why there's a relative min, why it's concave up, check out our chapter 3 contents, because nothing has changed. The only difference in this problem, ln is there, so the derivative we need to know how to take of ln. All right, that was awesome. See you next time. As always, peace.